Today we're going to talk about radical notation and rational exponents. A radical notation is this little root symbol, and this one is the square root symbol. The square root of a number is the value that when multiplied by itself gives that number back. For instance, if we have 5 squared, we know is equal to 25, so the square root of 25 is equal to 5. The square root operation is the inverse operation of squaring a number. Square root is always positive, and the number under the root needs to be positive to obtain a real number result. Remember when we were first talking though, we had the square root of -1 is equal to I. That's an imaginary number, and when we have that only works for square roots of negative numbers. In general, we want real number results, so the root, what's under the root, needs to be positive. Cube root, this number here is the cube root because it's got the little 3 there, is the value you need to multiply by itself 3 times to obtain the number. So 3 cubed is equal to 27, so the cube root of 27 is equal to 3. What about the cube root of -27? Is there a number we can multiply by 3 times and get -27? We know that multiplying 3 by itself 3 times is 27. What if we multiply it by -3? -3 times -3 times -3 is actually -27 because negative times negative is positive, and then another negative makes it negative. So the cube root of -27 is equal to -3. Let's evaluate. So now we have the 4th root. So this is asking us, we want something to the 4th power, something times itself 4 times, that is equal to 625. If we have the number 5, five times 5 is 25, times another 5 is 125, times another 5 is 625. So the 4th root of 625 is 5 because 5 to the 4th is equal to 625. This one we have the 5th root, so we need to multiply by something by itself 5 times, and that's equal to -32. Notice we have that negative in there again, and it is an odd index. We'll talk about index in just a second. It is an odd index, so that means that we can do that. So we're going to have negatives. If you think about it, negative times negative is positive, times another negative would be negative, times another negative would be positive, times the last negative would be negative. And then 32 is a pretty small number, so let's start with 2 and see if that works out. So 2 times 2 is 4, times 2 more is 8, times 2 more is 16, times 2 more is 32. So that is true. -2 to the 5th power. Notice the -2 is our base and the 5th power is the power, is equal to -32. So that means that the 5th root of -32 is -2. The radicand is the part of the expression that's under the radical symbol. So the radicand is this A part. The index that determines what kind of root it is the little number in the hook of the radical symbol. If there's no number there, if it just looks like this, the index here is 2. So if it's just this, the index equals 2. N is the index and A is the radicand. So let's look at these. The square root of 5, the radicand is 5, and the index, there's nothing there. There's no number there, so like I just said, the index is 2. The cube root of a plus b is under the radical symbol, so a plus b is the radicand, and the index is 3 because that's what's in the little hook. These two, the radicand for these two is the same. This is 5 times the square root of x. This is the 5th root of x. The radicand is the same. The radicand is x for both of them. X is the only thing under the radical symbol. But this is 5 times the square root of x. There's no index here, so it's 2, just like we talked about up here. This one is the 5th root of x, so the 5 is in the hook, so the index is 5 for that one. Rational exponent form. We use rational exponent form when we need to manipulate things with different indices, and we want in the same base. The other thing we use rational exponent form is sometimes it's just easier to simplify your exponents. So the nth root of a to the m, there should be an m there. The nth root of a to the m is equal to a m over n. So the m is going to be the numerator of the fraction exponent, and n, the index, is the same as the denominator. This works out when you think about it because multiplication and division are inverse operations. To get rid of multiplication, you divide, and to get rid of exponents, you take the roots. So a rational exponent is undoing the exponents. So this we just want to convert to exponent form. So we have our base is 3, the exponent is 5 for the numerator and 4 for the denominator. 5 is the exponent on the 3 and 4 is the index, 3 to the 5/4 power. The square root of p, we have p is the base, that's our radicand, and then the exponent on p is 1, and the index on this one, because there's no number, is 2. So the square root of p is equal to p to the 1/2. We'll do these two last. The radicand for this one is x plus y. Because it's under the radical symbol, we have to do the whole thing. The exponent on the x plus y is 1. And then the index of the radical is 3. So it's x plus y to the 1/3 power. This one is 2 times the 4th root of x cubed. So we have 2 times the 4th root of x cubed. So x to the 3/4 power. And then you can just write it 2x to the 3/4. These last two, we have 1 over. So remember, when it was 1 over, we ended up with a negative exponent. So we would have, to start with, we could have 1 over, I forgot some equal signs. Let's put our equal signs in there. 1 over g to the 4/3 power. 4 was the exponent, 3 was the index, but then let's write it with a negative exponent. That becomes g to the negative 4/3 thirds power. This last one, that u minus 2v is our base. Our exponent was 4, but we're going to make it negative because we want to bring it to the numerator. And the negative 4, and our index was 7. So 1 over the 7th root of u minus 2v all to the 4th is u minus 2v to the negative 4/7. Now we want to convert the other way. So the 3 to the 2/3 is going to be the cube root, so we put the 3 in the little hook, of 3, that was our base of our exponent, squared, which is the cube root of 9, if you want to go that far. You don't have to. All we're doing is converting right now. 7 to the negative 1/2, so that's 1 over 7 to the 1/2 power, and the 1/2 power is the square root, so that's 1 over the square root of 7. 3 times x to the 2/5 power. The base is only x, right? So we have to do that to the 5/2. So we have 3 times the 5th root of x squared. The 3 just stays along. X is what has the exponent, which is 5. X to the 2/5 is the 5th root of x squared. Same thing with this one. The 4 is multiplied to x to the negative 2/5. So we have 4 times, the negative makes it go 1 over, the 5th root of x squared, which is the same as saying 4 over the 5th root of x squared. A plus b to the 4/5, the a plus b is our whole base, so that's going to be the whole thing that's under the radicand. So that's the 5th root of a plus b. Because we have an exponent other than 1, we have to put a plus b in parentheses to the 4th power. So that says the 5th root of a plus b all to the 4th. And the last one is for the 5th root, b to the 5/7 is equal to the 5th root of b to the 7th. Now we want to evaluate some expressions. There's a couple different methods we can do this. We want to we'll rewrite this as the 4th root of 16 to the 3rd. If we had our calculator, we could do 16 to the 3rd, which is a really big number, and then take the 4th root of that. But we can do this without using a calculator. The first thing we want to do is take the root, because the root makes things smaller. So the 4th root of 16 is equal to 2. Again, when you're writing out your notes and you're writing out your workbook, make sure you write all these steps so that you know where all these values are coming from. So the 4th root of 16 is 2, so we can replace the 4th root of 16 here with 2, and we still have that exponent of 3. So then we can do 2 to the 3rd, which is equal to 8. So let's try this one. This is the cube root of 125 squared. The cube root of 125, what times itself 3 times is 125? That's 5. So the cube root of 125 is 5, so that's 5 squared, which is 25. We have 81 to the negative 3/4 power. So that becomes 1 over 81 to the 3/4 power. Remember, we just flip it over and make the exponent positive. So that's 1 over the 4th root of 81 to the 3rd. The 4th root of 81 is 3, because 3 times 3 times 3 times 3 is 81. So the 4th root of 81 is 3, so we're going to replace the 4th root of 81 with 3 here. And we have 3 cubed, which is 1 over 27. The last thing we're going to do is approximate radical expressions between two consecutive integers. Now, consecutive means in a row. So 2 and 3 are consecutive integers. 6 and 7 are consecutive integers. There's 2 things in a row. What you want to do is, if we have a square root, we want to look for perfect squares. So our perfect squares, so 1 squared is equal to 1, 2 squared is equal to 4, 3 squared is equal to 9, 4 squared is equal to 16, 5 squared is equal to 25, 6 squared is equal to 36, 7 squared is equal to 49, 8 squared is equal to 64, 9 squared is equal to 81, and 10 squared is equal to 100. These are all the perfect squares you should know off the top of your head. So now when we want to approximate the square root of 10, 10 is between 9 and 16. So the square root of 10 is between the square root of 9 so the square root of 9 is less than the square root of 10, and that's less than the square root of 16. But we know that the square root of 9 is 3, so that's less than the square root of 10. And we know that the square root of 16 is 4. 3 and 4 are consecutive integers, and the square root of 10 is between 3 and 4. In fact, the square root of 10 is closer to 3 than it is to 4 because 9 is closer to 10. So looking at the square root of 56, we still want perfect squares because this is a square root, and we want to find the 2 that 56 is between, the 2 next to each other. So 56 is between 49 and 64. So the square root of 56 is between the square root of 49 and the square root of 64. Again, we know the square root of 49 is 7, and that's less than the square root of 56, and that's less than the square root of 64, which is 8. So the square root of 56 is between 7 and 8. And it's pretty much right in the middle of 7 and 8, so it's probably about 7.5 or a little bit more. The cube root of 36, these were square roots, so we were looking at perfect squares. This is a cube root, so we have to look at perfect cubes. So let's erase that stuff and let's look for perfect cubes. Perfect cubes, we have 1 cubed is 1, 2 cubed is equal to 8. 3 cubed is equal to 27. 4 cubed is equal to 64. 5 cubed is equal to 125. So these are all the perfect cubes you should know when evaluating your stuff in the workbook or on exams. So 36 is between 27 and 64. So the cube root of 27 is less than the cube root of 36, which is less than the cube root of 64. But if we evaluate, the cube root of 27 is 3, and that's less than the cube root of 36, which is less than the cube root of 64 when we evaluate as 4. 3 and 4 again are consecutive integers, so 3 is less than the cube root of 36, which is less than 4. So the cube root of 36 is somewhere between 3 and 4. Again, it's closer to 3 than it is to 4. This last one, we have the fourth root of 100. This is a fourth root, so we need perfect fourth powers. So let's erase this. Remember, if you didn't get it all down, you can rewind and get it all down again. So perfect fourth powers. One to the fourth is equal to 1. 2 to the fourth is equal to 16. 3 to the fourth is equal to 81. 4 to the fourth is equal to 128. No. 256. Sorry about that. So 100 is between 81 and 256. So we're going to do the fourth root of 81 is less than the fourth root of 100, which is less than the fourth root of 256. The fourth root of 81, when we evaluate it, is equal to 3. And the fourth root of 256 is equal to 4. So the fourth root of 100 is between 3 and 4. Again, it's much closer to 3 than it is to 4. And then these are the perfect, you really should just know 3 to the 4th, especially because I messed up on 4 to the 4th. So those are the perfect powers you should know for the fourth powers. And last thing we want to do is do some evaluating. When we have expressions when a is equal to 3 and b is equal to -2, we're going to put 3 in for a and -2 in for b. So again, make sure you write out all your steps. So this is 4 times 3 squared. So that's 4 times 3 times 3, which is 4 times 9, which is 36. This is 4 times a, so 4 times 3 squared, which is 12. 4 times 3 is 12 squared, which is 12 squared is 144. So those two look really similar, but the bases are different, so that's why the problem is different. And the last one is 3. 2 was 3. A was 3, so 3 times 3 times b squared, so -2 squared. So we have 3 times 3 times negative 2 times negative 2. So that's 9 times negative 2 times negative 2 is positive 4. So 9 times 4, which is 36. That's it for today. See you tomorrow.